Welcome to Chapter 1, where we will dive into the discrete Fourier transform, or DFT. Before we get into the complex math, let's start with a crucial reminder about sampling. As you can see in Figure 1, to turn a real-world analog signal into something a computer can understand, a digital signal, we have to take snapshots of that signal at regular intervals. Think of it like taking a series of photos of a moving object. If you take them fast enough, you capture the essence of the motion. Mathematically, we represent this sampling process by multiplying our continuous signal xt with a Dirac comb, a sequence of impulses separated by a sampling period, t. This transforms our continuous time signal into a discrete time signal. In the frequency domain, this multiplication is equivalent to a convolution, which effectively creates copies of the original signal spectrum at every multiple of the sampling frequency, phi. This brings us to a fundamental concept. Sampling in the time domain causes periodization in the frequency domain. As the formula shows, the resulting spectrum, say, f, is now periodic with a period of phi. It's like an infinite hallway of mirrors where the original spectrum is reflected over and over again. Understanding this periodicity is key to preventing information loss. To ensure we don't lose information, we look to Shannon's sampling theorem. Imagine a signal that is band-limited, meaning its highest frequency component is fmax. To reconstruct this signal perfectly from its samples, we need to choose our sampling rate very carefully, as we'll see on the next slide. If our sampling frequency is more than twice the maximum frequency, the Nyquist rate, the spectral copies remain separate, and we can use a low-pass filter to recover the original signal perfectly. However, if we sample too slowly, as shown in the bottom diagram, these spectral copies overlap. This overlap is known as aliasing or spectrum folding. And once it happens, the original information is permanently distorted and cannot be recovered. In practice, we use a sample and hold circuit at the input of an analog to digital converter. This circuit has two jobs. First, it catches the exact voltage level at a specific moment, and second, it holds that value steady while the converter does the heavy lifting of turning that voltage into a binary number. Without this stability, the resulting digital data would be highly inaccurate. After sampling, the next step is quantification. While sampling makes time discrete, quantification makes the amplitude discrete. We take our sampled value and round it to the nearest level on a fixed grid. If the spacing between these levels is constant, we call it uniform quantification. Essentially, we are mapping an infinite range of possible voltages onto a finite set of digital codes. Because we are rounding the signal to fit a grid, we introduce a small error known as quantization noise. As shown here, the more bits we use, represented by n, the smaller the steps Q become, and the more accurate our digital representation will be. It's the difference between a grainy, low-resolution image and a sharp, high-definition one. Putting it all together, here is a typical analog-to-digital conversion chain. Notice the anti-aliasing low-pass filter at the very beginning. Its job is to block any frequencies higher than half our sampling rate before they can cause aliasing. From there, the signal is sampled, quantified, processed by a computer, and can eventually be smoothed back into an analog signal for the real world. Now, let's refresh our memory on Fourier analysis. For a periodic signal with a period t, we use the Fourier series. This allows us to decompose a complex repeating wave into a sum of simple sines and cosines. Each Cn coefficient tells us how much of a specific frequency component exists within that signal. We can express this same decomposition using real-valued sines and cosines instead of complex exponentials. Here, A0 represents the DC or average value, while an NBN represent the amplitudes of the oscillating parts. The key takeaway here is that traditional Fourier series are strictly for signals that repeat forever. But what if the signal isn't periodic? We simply imagine that the period t is infinitely long. As t goes to infinity, the discrete frequency spikes of the Fourier series merge into a continuous function called the Fourier transform. This gives us a way to analyze the frequency content of any arbitrary, non-repeating signal. When we apply the Fourier transform to a signal that has been sampled, we get the discrete time Fourier transform, or DTFT, by substituting our sampled impulse train into the Fourier integral. We arrive at a formula where the continuous integral is replaced by a sum of the discrete samples multiplied by complex exponentials. The result of the DTFT is a spectrum that is periodic with the sampling frequency, phi. While the input x, n, is a discrete sequence of numbers, the resulting frequency f is still a continuous variable. This creates a problem for computers. How do you calculate something that exists an infinite number of frequency points? The solution is the discrete Fourier transform, or DFT. Instead of looking at every possible frequency, we only calculate the spectrum at n specific regularly spaced points. We define a frequency step, delta f, which is the sampling frequency divided by n. This makes the math computer-friendly by mapping a sequence of n time samples to a sequence of n frequency values. Looking closer at the DFT formula, we see it relates n time domain samples to n frequency domain bins. A very important side effect to remember is that by sampling the frequency spectrum, we are mathematically implying that the time domain signal is also periodic. In the world of the DFT, the signal we are analyzing is treated as if it repeats every n samples. Figure 13 beautifully summarizes these relationships. Sampling in time makes the frequency spectrum periodic. Sampling in frequency makes the time domain signal periodic. This duality is the cornerstone of digital signal processing. To have a finite, discrete representation in one domain, you inevitably introduce periodicity in the other. To get back to the time domain, we use the inverse DFT. The DFT also follows several useful mathematical rules, such as linearity and time shifting. One of the most important for engineers is the energy conservation property, also known as Percival's theorem, which states that the total energy of the signal remains the same whether you measure it in time or frequency. A quick pro tip: if you need a smoother looking spectrum, you can use zero padding, adding zeros to the end of your signal, to calculate the DFT at more points. Also, it's important to note that while we've been discussing the DFT, in practice, we almost always use a much faster version called the FFT, which we will look at next. The fast Fourier transform, or FFT, was a breakthrough because it drastically reduced the number of calculations needed. A standard DFT requires n squared operations, but the FFT only needs n times the log of n. For a 1024-point signal, the FFT can be 100 times faster. This efficiency is what allows your smartphone and computer to process audio and video in real time. To understand how the FFT works, let's look at an 8-point example. We use a twiddle factor W sub n, which represents a step around the unit circle in the complex plane. These factors have symmetry and periodicity properties, like the fact that rotating halfway around the circle is the same as multiplying by -1, that allow us to recycle calculations. By arranging the DFT into a matrix, we can see many redundant patterns. The FFT algorithm exploits this by splitting the endpoint sequence into two smaller sequences, one containing the even index samples and one containing the odd index samples. This divide and conquer approach is the secret to its speed. Through some algebraic manipulation, we can show that an endpoint DFT can be expressed as a combination of two smaller p-point DFTs, one for the even terms, UK, and one for the odd terms, VK. This reduces the complexity significantly because we're breaking a large problem into smaller, manageable pieces. The real magic happens because of the symmetry in the twiddle factors. The same values used to calculate the first half of the spectrum can be reused with a simple sign change to calculate the second half. This plus or minus relationship is why we often see butterfly diagrams when looking at FFT architectures. By repeating this splitting process, dividing the 8-point DFT into 4-point DFTs, and then into 2-point DFTs, we reach a point where the calculations are trivial. This diagram shows the 3 stages of an 8-point FFT. It's like a tournament bracket where the data competes and combines at each level until we get the final frequency output. In the final implementation, the inputs are often reordered using bit reversal to make the algorithm more efficient. One final piece of practical advice: always use a waiting window like hamming or panning rather than just cutting your signal off abruptly. This prevents spectral leakage and ensures the spectrum you see is as close to reality as possible. Thank you for your attention.